Okay, so our third session will be dedicated to the Starshot project and potential instrumentation. And I'll just give a brief introduction to the theme of this session. It's often said that it's not wise to look for keys under the lamppost. However, many people do that because that's the only place where you can easily search for them. In the case of intelligent life, it certainly is not the case that if it's very advanced civilizations, it should be restricted to the environments of stars. But for primitive life, we believe that liquid water is necessary, and therefore being close to a star is an important ingredient of an environment that can keep water at the right temperature. And so the good news is that the existence of life around the low-mass stars can be searched in our environment. And the nearest star system is Alpha Centauri, as we heard yesterday. Proxima Centauri, the third star in that system, has a planet in the habitable zone at roughly 5% of the Earth-Sun distance from that star. The issue is that this star is 4 light years away, so it takes light 4 years to get us. If we ever want to visit it, it will take much longer. The fundamental question is whether whether Proxima b has an atmosphere. That we can analyze remotely. And there are a number of things we can do with telescopes on Earth that would not require visiting the planet. And in fact, we will discuss in this session things that can be done by a flyby that cannot be done remotely. But with the James Webb Space Telescope, in principle, we can probe whether the planet has an atmosphere, and that's just by looking at the phases of that planet as it goes around the star. We're seeing different parts of its day side as it moves around, and therefore there should be some modulation of the light depending on the temperature contrast between the day side and the night side. And so just by looking at the day-night contrast, and this is work with Laura Kreitberg that we did, you can actually tell whether there is heat distribution on this rock that we call Proxima b. If there is no atmosphere, the temperature contrast would be largest. But if there is an atmosphere or an ocean there, it would moderate the temperature contrast. And therefore, as you compare the color of the planet as it moves around the star, the color will be modulated. The temperature will vary depending on the phase of the planet in its orbit. And from that, you can infer what the temperature contrast between the day and the night sides is. And so that can be done remotely. But the project of Starshot that was announced about a year ago, a little bit longer than a year ago, is to actually visit those planets and potentially detect them directly. And so the goal is to fly a probe very close to a potential planet and figure out whether it has life, what the color of the planet is. Is it green? Does it have vegetation? Is it blue? Does it have oceans? Or is it desert-like? And that's just one instrument that one can imagine. But in this session, we will discuss all kinds of other instruments that can be used. And the goal is to launch a gram-scale device that has all the important electronics attached and fly by the planet. And the technology that we plan to use involves a light beam that is pushing on a sail, because to visit the nearest star within our lifetime, let's say in 20 years, the spacecraft needs to move at 1/5 of the speed of light. And it's non-trivial. We converge on only one technology that can do that. In analogy with getting married, you just need one solution to the problem you have. So having that technology is good enough for us. And that technology is using a very powerful laser beam that is pushing on a lightweight sail. And since the light can reach the sail even as it accelerates close to the speed of light, and since we leave the fuel behind, we can, in principle, reach very high speeds. And the structure of the sail is still being discussed. It could be a sphere that is riding on a hollow laser beam, and by that, we maintain stability. You can think of the sail as a spherical ball that is an enlarged ping pong ball that is riding on the beam. And so there are various technological aspects to this project, and the reason that it looks feasible is because of the miniaturization of electronics these days. If you look at a cell phone and you strip it from its case and the human interface, the electronics weighs a few grams, and you can imagine packing a camera, a navigation device, a communication device into a few grams. And you can imagine also using material science that evolved a lot recently to make sails that are lightweight, that weigh of order a gram, with a surface area of a few meters. And then finally, constructing laser beams that are powerful enough to push on a sail and bring it close to the speed of light. You need roughly the amount of energy that was needed for the space shuttle to lift off over the same amount of time, a few minutes. So we are talking about of order 50 gigawatt beam. And the technology, is using the same principle as sailboats. We are just pushing on the sail. Instead of using a wind, we are using light. And of course, there are many phases to that mission. The first would be to construct a demonstration that the technology works. So in the next 5 years, the goal would be to test the feasibility of this technology, whether we can combine small laser beams to a single coherent beam, whether we can construct a sail that is made of a material that is lightweight and nevertheless does not absorb more than 1 part in 100,000 of the light, because otherwise it will burn up. And then whether we can construct a beamer that is of the right scale for this project. And as we move beyond the next 5 years, the idea would be to build a prototype that will get bigger in scale, and eventually the final system that will have roughly an array of beamers on the scale of 1 kilometer or so. And then there would be a launch in the long term, decades from now. The launch will take a few minutes, and one can launch many such small spacecraft. So it's a very different concept where each of the spacecraft is relatively cheap, and most of the cost is in the infrastructure, in the beamer. And one can imagine sending hundreds of those. And then it takes a few minutes to reach 1/5 of the speed of light. Then the cruise takes a couple of decades to reach Proxima b, for example, or other stars. And then there is an encounter with the planet. Data will be sent back to Earth and reach us 4 years later. And we can imagine other civilizations that had much more time than we did may have already mastered that technology. So this connects to the previous session, which is SETI. In principle, we can search for light beams that are sweeping across the sky, and they would appear as flashes of light. And the question is, are we seeing them? Do we have hopes to see them? And they may be in the radio or in the optical. You can imagine a transportation system between Earth and Mars on another planetary system that looks analogous to that of the solar system, and then figure out the parameters of the beam and so forth that would be related to that. And it might even be that these enigmatic fast radio bursts that we see are related to an artificial origin for this reason, that they relate to beams of light used for propulsion. And in that context, one imagines using covering the surface of the planet with a lot of solar cells and using that energy to create the powerful beam of radiation. Now, aside from that, I wanted to mention also that the search for life in the solar system is very interesting in solar system environments, because obviously to reach 20% of the speed of light will require a huge effort, a very challenging technological effort. But along the way, as we make progress, we will have intermediate steps. And Within the solar system, even if we improve the speed of current rockets, current technology, by an order of magnitude to hundreds of kilometers per second, that would have a dramatic impact, because in principle, we can shorten the time it takes to reach targets of interest in the solar system. One example is the plumes of Enceladus that may potentially harbor evidence for life. These plumes are coming from an ocean under the ice. If one imagines flying through them, one can collect a sample of the molecules there, look for amino acids, and figure out if life there is the same as life on Earth, and that would have a dramatic impact on our understanding. So if one develops a way of sending a probe that would reach those plumes quickly, then in principle, you can even correct in real time. You can send one probe, collect data, and then equip the next probe differently in a way to get additional data, rather than send a mission that will take 20 years to complete. And that's a very different method of gaining information about potential sites of interest within the solar system. And we will discuss that. And also the fact that the spacecraft are relatively cheap allow us to send a lot of them, and therefore a variety of spacecraft to different locations with different purposes. Now, we could also search not just for primitive life, also for intelligent life. And there are exotic signals that one may think about. I'll just mention a few very quickly. So before getting to intelligent life, we should contemplate the possibility that life could be delivered between different planets, transferred from one planet to another. That's called Panspermia. And the TRAPPIST-1 system is a very good illustration of that. We have a much more densely packed planetary system in the TRAPPIST-1, around the TRAPPIST-1 star. And it turns out, if you just do a simple calculation, and we did that with Manasvi Lingam, that the transfer of life in that system is 100 times shorter than between Earth and Mars, if you do it with rocks. And just simply because planets are closer together, and as a result, the travel time is shorter, but also the chance of a rock landing on a target planet is higher because of the compact configuration. And in principle, if we visit environments and we figure out the types of life forms that we find there to be similar, then that could educate us as to whether panspermia takes place. In terms of intelligent life, we can look for molecules different from oxygen, molecules that are produced artificially, for example, by industrial pollution, and also terraforming activities of other civilizations. So that connects to the SETI session. In terms of molecules, we produce a certain contamination of the atmosphere, but in principle, one can imagine artificial contamination of atmospheres of planets for the purpose of creating a greenhouse effect, for example, on a planet that is otherwise too cold. One can look for spectral edges. We all know about the red edge of plants, but in principle, there could be artificial edges due to photovoltaic cells that also exhibit a very sharp change in reflectance at a particular wavelength. And as a planet goes around the star, we would obviously see different phases of it. These are just general comments, and we will have a lengthy discussion in this session by the speakers and also later on by the panel. And I would like to invite Phil Lubin to start the discussion with his talk.